three-dimensional problem with three variables, so x, y, and z, it just changes the problem in the sense that it's no longer a line, because a line was in a two-dimensional plane, x and y, so you get a straight line. Then the three-dimensional, what would that end up being? But the concepts are still the same. Everything that I described, when you're solving simultaneously with three variables, you're now just finding the intersection of what three variables mean. So the question is, what does three variables mean? Once you understand what it looks like, the method's still the same. Now, for Exercise2G, all you're doing is calculator. Everything is calculator work at this point, but your understanding is from 2F. Okay, so let's have a look. Three variables. This is your matrices for three variables. So very similar to your 2x2 matrix. It was A, B, C, D, and you multiplied that to matrix XY because you got an XY coordinate, and it gave you, I don't know, let's go E, F, G, matrix B, yeah? So matrix A times matrix X equals to matrix B. That's what you were doing, and that was simultaneous of, when you have X and Y, simultaneous of straight line equations, X variable below Y variable. So it was two straight lines, and you were analyzing what happens when you have two straight lines. It's either parallel, when you have one intersection, it's a unique solution, or it's the same line and it's infinitely many. Yeah? So the question is, what does x, y, z look like when you have three variables? In this case here, it's still the same idea. If you were solving for it, you still need an A inverse. So the only difference here is that you don't need an A inverse formula at Year 12 methods. When you get to the first year uni, you will learn the method to do this. It's called reduced row echelon, which in your calculator does have RREF. It teaches you how to reduce this to solve for x. Okay, so at the end of the day, you're still trying to find the identity matrix, and there is a way for you to find the A inverse, but it's not part of our course. So how do you find A inverse? Calculator. I'll show you how to do it later. Okay? So here we go. Same idea. What does it mean when you have three variables? Because you're doing with 3D planes, or like 3D or 3 dimensions, what you're actually solving for is not a line anymore, but take a line, if you draw it in 3D, it becomes a plane. And a plane means like a platform, like a sheet, okay? Because when you think about it in 2 dimensions, it made sense that that was a straight line. But you put in a 3-dimensional shape, this straight line now ends up being, I'll do it in blue so you can see the difference. If that was your straight line, then extending it along this axis, you get a sheet. See what I'm doing there? So if I just delete that z-axis, that's your blue line. That's your straight line equation. But if I put in another axis, which is a 3-dimensional shape, so you put in another axis, that's my z-axis, that's my x, that's my y. Then what happens now is if you draw that blue line and extend it along the direction of the z-axis, and you connect them all together, you get a sheet. Okay, so you get this 3-dimensional sheet. Okay, so when you solve for 3 equations, okay, 3-dimensional equations where you have x, y, and z, and 3 different equations, you're actually solving for now 3 planes, 3 sheets for when they intersect. And that's all you're really doing. Now these are the possibilities, so you can copy this down. These are the possibilities for what you can get. See, if there are 3 planes, they can all cross at one point. Okay, so you can see if you have a shape that cuts diagonally, okay, so if it's diagonal, they're crossing along that plane. True? It's like a simple line. But if I show you with 2 pieces of paper, if I'll borrow these 2. Yeah, I'll just take it. See this? If I slip this through, like through there, the part where they intersect would be this entire white sheet here. That line there, that's a sheet. True? But if I put in a third point, if I put a third plane, I put it like right there, then where do they all intersect? It's only one point. You can picture that. So if I do another sheet, sort of like, I don't know how to do it. It's like that. If you can sort of picture that, where do they all intersect? There's only one point they all intersect. See what I mean? There's only that one point where they all intersect. Okay, it's all about 3 planes equaling to each other, not one line. So, because it's just, I don't know. Thank you. If you have one line, so you can either have one intersection at a point with 3 planes or 3 sheets. You can have, like what I just showed you just now, it's an entire line. So if they all cross through a particular line. I don't know what happened just then. Anyways, so you have intersection of a line, so it either crosses through an entire line there, or no intersections. Okay, now the no intersection is interesting because we're interested in 3 planes where they all cross the same point. So this is where they don't cross at all, either any of them, they're all parallel, or 2 of them are parallel and 1 intersects both, but that means that they don't all intersect, so hence no common intersection. Okay, because we're interested in 3 of them now. 3 variables, a 3 by 3 matrix means 3 planes, 3 variables. Yeah? And so in this case again, they're all intersecting differently. This diagonal intersects with this shape, and it also intersects with this shape, but it doesn't intersect with every single shape. Okay, so you can see that this connects with, this plane connects with this one connects with this one connects with this one. So they don't all have a common intersection. So these are your 3 no intersections. Or you can have an intersection of a line, or you can have an intersection of a point. And unlike your 2D, your 2D was either they have 1 intersection, or they're parallel. Those are the only times that they can be like not intersecting, or they're intersecting exactly the same lines. Okay? So the theory is exactly the same. Everything's still the same. The only difference is you have to think of it as 3D shapes, and these are the only possibilities you can have. No solutions, have many of them. And you can only have either a line or a point. Okay. That's the difference. So this is kind of like an infinitely many. Depending on how long the line is, if there's no domain, it's infinitely many on this particular line. Okay. All right, so how do you answer these questions here? It's exactly the same technique. So if you were to solve this, you can see here I've got how many equations? I've got 1 equation. I've got 2 equations, I've got 3 equations. So how many variables do I have? I've got x, y, and z. 3 variables. So that means this is a 3-dimensional shape, and that means it's a plane or a sheet. This is a sheet, that's a sheet. So that means I've got 3 planes, and now I'm trying to solve simultaneous equations. You can do this by hand, you do this by calculator. Now in your textbook, all the solutions, the work solutions, if you look up on Schoology, the work solutions are all done manually. Okay? So it is possible to do it manually. You want to do a bit of both. You want to be able to solve for 3 dimensions or simultaneous equations with 3 linear lines, 3 variables. You want to be able to do that by hand, but you also need to be able to do it efficiently on a calculator. Yep, what's a parameter? A parameter, oh, good question. Parameter, now here says describe these solutions through a parameter, right? I'll give you a quick example. Just going back to 2F. What is a parameter? Now, parameter, we use that all the time. So, for example, straight line equations. Y equals mx plus c. M and c are parameters. They are constant in that particular case, but they vary, meaning that they can be any number. So, for example, if I said m equals 2 and c equals 8, then in this particular line, I now have y equals 2x plus 8. But you see, x and y varies. X can be 1, x can be 2, x can be 3, it varies. That's why we call that a variable. But what's constant is 2 and 8. But it doesn't have to be 2 and 8 because I made up those parameters. So parameters will stay constant for this particular linear equation. Then if you change that to 3 and 8, then you get another parameter or another equation. So M and C are called parameters. They're kind of like your variables, except variables always change. Parameters don't in that particular equation. So if you think about quadratic equation, y equals ax squared plus bx plus c, a, b, and c are parameters. X and y are variables. Yep.
So in this case, the x called parameters is x plus.
Yes. Okay, so I'll do an example here. Let's say I gave you y equals to 3x plus 1, okay, and I say the other equation is, let's say, what's it? Minus 1 plus y equals 3x, right? And I tell you to solve this equation. Now we know that if we rearrange both of these, they're the same equation, 3x plus 1, and you've got y equals to 3x plus 1 again, true? Now in that case, because they both have the same lines, they have infinitely many solutions. So they're the exact same lines, so they cross at infinitely many points. Now, if I asked you, well, which points do I have that they intersect? You can say, well, when x equals 1, you would have y equals to 3 times 1 plus 1, and you would say that's 4. When x equals 2, you would say, well, y would then be 3 times 2 plus 1, and you get 7. So the coordinates of intersection so far, you would say it's when x is 1, y is 4. When x is 2, y is 7. These are two possible answers, but what you don't want to do is to sit there and trial and error and write out every single answer. So when they say describe your solutions, these are my solutions, describe them using a parameter, what they're saying is instead of choosing 1, instead of choosing 2, choose a letter. So I can use that letter. That parameter could be any letter. It could be A, B, C, T. They like to use T. We used to use lambda, this symbol here. That's lambda to sort of denote a parameter, but you could call it anything you want. You could call it A. So if I said now, okay, let's call X, instead of 1 and 2, if I called it A, then Y will now equal to 3 times A plus 1. So what does that mean? That means my answer would be whatever X is, my point of solution would be that. See how that is a better answer? That's a better answer to summarize all my solutions. To describe my solutions using a parameter. This is describing my infinitely many solutions with y equals 3x plus 1. Instead of writing 1, 4, 2, 7, you carry on, this describes everything, where A is an element of real numbers. A can be anything. See, but that's what a parameter is. A parameter is saying, instead of doing 1, 4, 2, 7, there has to be a better way to describe it. And it's not a variable, because the variables here, x and y, these are my variables. We had to use what we call a parameter. That's an example. Okay, so that summarizes my infinitely many solutions.
You just use x. Like it's the same thing.
You're just
I know essentially, I know what you mean. Mathematical language-wise, it's not. It doesn't make sense because if you're saying when x is 1, then x is 1. Like, I know what you're saying, it's true. You could say x and y. Good. You could say x and then 3y plus 1. 3x plus 1, sorry. You can do that. I'm just not recommending you to do that. It's just not how we do it mathematically. So when they say use a parameter, use anything, you can use lambda. That's the common technique that we've always used in the past. So in the exam, if they use lambda, they're trying to tell you it's a parameter. Okay? But I'm just saying parameter can be any letter. It doesn't have to be lambda. It could be A, it could be C, it could be T. Yeah? So in this case here, how do you answer this question? It's the same idea. What I did was I solved for x. I got x. I let that equal to a parameter, and then I got y. Now, you can do this on a calculator, or you can do it by hand. I did it on a calculator. I typed in solve, and this is what you get. See that C1? Those C1s are parameters. Okay, these are all my parameters here. So I said, I've got my 3 equations, my 3 variables, and I said solve for x, y, and z. And they told me, well, x will equal to this, y will equal to this, and z equals to that. So what I'll do is I'll say, all right, well, why don't I let z equal to lambda, a parameter? If I do that, if z is my lambda, then that means here, y equals to 5 times, C1 is my lambda, so lambda minus 3, and then this one would be x equals to negative of 13 lambda minus 43. Okay, so you can see this is just an example. Lambda is a parameter, but this is your answer. This is all you have to write to describe your solutions parameter. I just said, what if lambda was 4? So what if my parameter was 4? Then now I've got a description. I put 4 in, and I get my equations, or my coordinate of solution. Yeah, but this here describes all my possible answers because we have infinitely many solutions. That's what's required. Okay, so exercise 2G, what are you really doing? Calculator work, solving for x, y, and z. But describing infinitely many solutions, you can use a parameter. I use lambda. You can use A, B, C, D, T, whatever you want to call it. Okay, the theory comes from 2 ends. Yeah, so just understanding it's a plane of intersection, not a line anymore. So when you have 3 dimensions, a 3 by 3 matrix, this is now a 3-dimensional shape rather than a 2D. That's the only difference. Okay, that's why I told you I said I can teach chapter 2 in one lesson, because all you needed to understand was 2F. 2F was the key skill. A, B, C, D was really nothing. Okay, it's just E and F. Yep.
I did a little check exercise for you, a little brackets.
That was braces.
Yeah.
Yes. Oh, you mean like to type in the calculator? No, I actually didn't type in the calculator as square brackets. I just wrote X, comma X, comma Y, comma Z, and when I press enter, that's what happened. Yeah. Okay. Cool is. Now, if you're interested in doing it by hand, that's what in the back. All the solutions are there to do it by hand. Obviously, you can see that if I just added these two together, you'd be able to find y. If you can find y, you can solve it. So you can see if I call this equation 1, 2, and 3, you can say equation 2 plus equation 3, and what you'll get is 2y plus z equals 7, 2y minus z equals 5. If you add those two together, you get 4y, and this cancels out to be 0, equals 12, so y has to equal to 3. So now that you know y equals 3, you can sub it back in and solve for z. Okay, if you can solve for y and z, then you can solve for x. Yeah, so most of these problems here, you can do it by hand. And that's why in your textbook, they've designed it so you can do it by hand. I want you to do both. So I want you to do a bit of like hand, so that you know that you can solve even the harder ones, and then do it in a calculator to be more efficient. So you can use lambda, learn to use the parameter, learn to think, is it a point, or do I have a line? So infinitely many solutions, or do I have no solutions? Okay, your job is to determine those 3 different scenarios for a 3D shape.
You don't have to
no. But I guess if you had to, I haven't seen, but if you had to, you'd just have to find the x, y, and z intercepts. So the only difference here is if I draw a 3D line, if I want to, let's call this, I think this is your normally z. I can't remember what the traditional is actually. It might be, whoops, x and y. But let's say if you want to find z-axis intercept. How do you find the z-axis intercept logically? How would you find it?
everything else equals 0.
Logically, y would equal 0, and x equals 0, z equals 0. Find those points, and if you connect those points, you will get a shape. And that shape is roughly the plane. Okay, so if I gave you, let's say, x plus y plus z equals to 4, then you can actually look at this and say, well, what does that shape look like? Find out the z-intercept. So here we go. Z-intercept would occur when x is 0, when y is 0, and z, I don't know. So if you sub that in, you get 0 plus z equals 4. So that means that 0, 0, 4, that's my z-intercept, 0, 0, 4. Then you want to find your y-intercept. So y-intercept will be the same thing. It will be x is 0, y I don't know, z is 0. And again, same thing, you get 0 plus y plus 0 equals 4. So you end up with 4, 4. This is your plane, roughly. That's what x plus y plus z equals 4 roughly looks like. I've only just used 3 points, but you can see it's a sheet that carries on from here onwards. Okay, it's over on the slant. So that's how you can sketch if you needed to. You've got to find your x, y, z intercepts. That way. Because it's a plane, it's a straight line, it's easier than doing curves. I think you only do curves in special. In this case, you're only doing straight lines. So you find x, y, z intercepts.
You also have to label the origin.
The origin.
When you're graphing.
Yeah, I don't normally, but I guess you could. It wouldn't hurt to put a 0 there.
Any marks.
I don't think so. I don't remember them asking you to draw a 3D plane. I don't think that's part of the methods course, but I'm just showing you if you were to, that's how you do it. Okay? There you go. That's exercise 2G. Thank you. We've got about 3 minutes left.